Here are three matrices that have already been reduced to row echelon form. Our goal is to describe the solution set corresponding to the system of equations represented by each matrix. In describing the solution set for this matrix, for example, we're also describing the solution set for any linear system whose augmented matrix has this as a row echelon form. So the focus here is on interpreting this form and using it to describe solution sets. We're not really talking about how to get a matrix into row echelon form. I'll leave links in the description to my lessons going over Gaussian elimination and Gauss-Jordan elimination that are all about that. Let's begin with this example. We see in this echelon form matrix there are three variables, since we have three columns to the left of the vertical bar. The vertical bar separates the variable coefficients from the constants. So we have three variables, x1, x2, and x3, and of course we've got these two constants, and we have two equations, an equation from row 1 and an equation from row 2. Here those equations are. Row 1 tells us that 1x1 minus x2 plus 3x3 is equal to 4. And row 2 tells us that x2 plus 6x3 is equal to 2. Remember, each entry here in the matrix is the coefficient of a variable. The entries in column 1 are the coefficients of x1. The entries in column 2 are the coefficients of x2, and so on. The numbers to the right of the vertical bar are the constants on the other side of each equation. In these two equations, x1 and x2 are what we would call leading variables, because they're the variables that appear first. So x3 is not a leading variable in this system, and that's indicated to us in the matrix because column 3 does not have a leading 1. We see that column 1 does have a leading 1, that's a 1 at the front of its row, and column 2 also has a leading 1. This 1 is at the front of its row. We don't count the 0 because it's 0. To say that the 1 is leading its row is to say that it's the first non-zero entry in the row. So again, x3 is not a leading variable because there is no leading 1 in that column corresponding to x3. Hence, x3 is what we call a free variable. It can be whatever it wants, and the remaining variables that aren't free can be calculated accordingly. Since x3 is free, typically we'll give it just an arbitrary parameter name like t. In this way, we parameterize the entire solution set in terms of this parameter t. If x3 is equal to t, then from equation 2, we can subtract 6x3 from both sides, and thus have that x2 equals 2 minus 6x3. But of course, x3 is just t, so 2 minus 6t. Now we can do a similar thing with equation 1. We can replace x3 with t, and we can replace x2 with 2 minus 6t. Thus, adding x2 to both sides and subtracting 3x3 from both sides, we have that x1 equals 4, and then plus x2, but x2 is 2 minus 6t, so plus 2 minus 6t. And then minus 3x3, but x3 is t, so minus 3t. Then 4 plus 2 is 6, and minus 6t minus 3t is minus 9t. And so the solution set can be described like this in terms of t. Any triple x1, x2, x3 of this form, where x3 is free to be whatever it likes, and x2 and x1 are calculated accordingly. Any triple like that is a solution to the system represented by this reduced matrix. And of course, any system of equations whose augmented matrix could be reduced to this row echelon form also has this as its solution set. That first example had infinitely many solutions, since x3 was a free variable. This next example has one unique solution. We see already that there are no free variables because each column has a leading one, so none of the variables are free. You might point out that column 4 does not have a leading one, but that's not relevant. When I say no column has a leading one, I specifically mean the columns that represent variables. Columns 1, 2, and 3 represent those variables x1, x2, and x3. Then, from these three rows, we get these three equations. Row 1 tells us that x1 plus 2x2 plus 3x3 is equal to 1. Row 2 tells us that x2 plus 2x3 is equal to negative 3. And row 3 tells us simply that x3 equals 4. Then we can plug x3 equals 4 into this equation to solve for x2, and then plug those known values for x3 and x2 into the first equation and solve for x1. Knowing that x3 equals 4, we can plug that into this equation and get that x2 plus 2 times 4, which is x2 plus 8, must equal negative 3. Hence, subtracting 8 from both sides, we find that x2 equals negative 11. Now we can plug negative 11 in for x2 in the first equation, and plug 4 in for x3. Thus, 2x2 is negative 22, and 3x3 is 12. So we have x1 minus 22 plus 12 equals 1. Hence, x1 equals 11. So this is the one unique solution to any system whose augmented matrix can be reduced to this echelon form. x1 equals 11, x2 equals negative 11, and x3 equals 4. Now moving on to our third and final example. In this case, we have 1, 2, 3, 4 variables. This fifth column, of course, represents the constants. The first 4 columns represent coefficients of those 4 variables. We're going to have just 2 equations. We have 3 rows, but the third row is all zeros, so that's not telling us anything. Row 1 tells us that x1 plus x2 plus 2x4 is equal to 1, and we see that there. Row 2 tells us that x2 plus 2x3 plus 3x4 is equal to negative 3. Columns 3 and 4 don't have leading ones, so the corresponding variables, x3 and x4, are free variables, and we will assign them to arbitrary parameters, say x3 equals s and x4 equals t. Then we can solve for x1 and x2 in these two equations and express them entirely in terms of these parameters, s and t. First, taking this equation and solving for x2, we would have negative 3 minus 2x3, but x3 is s, so that's minus 2s. Then also we'd have minus 3x4, but x4 is t, so that's minus 3t. So x2 is equal to this, which we could rewrite as minus 2s minus 3t minus 3, just to write this in alphabetical order, s then t, and then constants at the end. So that's x2 in terms of s and t. Now we can take the first equation and write x1 in terms of s and t. We'd have to subtract x2 from both sides, so we would have 1 minus x2. 1 minus this is x2 in terms of s and t. And then we'd have to subtract 2x4 from both sides. Subtracting 2x4 from both sides, well, x4 is t, so that's minus 2t. So x1 equals all of this stuff. Now we can distribute this negative and combine like terms. Then we have negative negative 2s, that's positive 2s. Negative negative 3t minus 2t is 3t minus 2t, so 1t. And then 1 minus negative 3 is 4. So this is x1 expressed in terms of s and t. So any ordered 4 tuple, x1, x2, x3, x4, of this form will be a solution to any system of linear equations whose augmented matrix can be reduced to this row echelon form. Again, in this case, we have infinitely many solutions because of the free variables, although in this example, we have 2 free variables instead of just 1. 1. So that's how to describe the solution set for the linear system corresponding to a matrix in echelon form. Let me know in the comments if you have any questions, and be sure to check out my linear algebra course and linear algebra exercises playlists in the description for more. Thanks for watching.
Stressed out, sweetie, I'm stressed out. Sounds like you've been stressed out. Tell me what you're stressed about. Stressed out, honey, I've been stressed out lately. Don't know what's what, don't know what I'm stressed about. Stressed out, sweetie, I'm stressed out. Sounds like you've been stressed out. Tell me what you're stressed about.